Welcome back to Inquisitive Kids. In this video, we will be learning about irrational numbers. So, Chapter 2, defining what are irrational numbers. Our course outline for this unit, Unit 2, would be first irrational numbers, the lesson we are doing right now. Then there will be 3 lessons on square and cube roots. Then we're going to learn about estimating real numbers, and then finally mixed calculations with roots. Our learning goals for this lesson is to understand the basic concept of irrational numbers, and we're going to be able to use a calculator to estimate the value of an irrational number. Combin is a student who has just entered the 8th grade. One weekend morning, his father asked him a math problem. He said, "There is a square wooden board with a side length of 6 centimeters. Its 4 right triangles are sawed off as shown in the figure. What is the area of the remaining board? Can you help Combin solve this problem?" So we know that the side length of this square is 6 centimeters long. So the side length of this large square is 6 centimeters long. And if we know that the base of this small triangle is 2 centimeters long, it means that the rest of this distance is 4 centimeters long. And we know that these 4 smaller triangles has to be the exact same, which means that their bases are the same. So this is also 2 centimeters long. And now we learned the Pythagorean theorem in the last unit, so we can use that to help us solve this problem. We have to find the side length of this smaller square. So 4 squared plus 2 squared equals 16 plus 4, which is the same thing as 20. And so let's say that this side is A. So A squared would equal 20 centimeters long. And now we have the answer to this problem because the formula to finding the area of a square is its side length, in this case A squared. And we already know that A squared equals 20, which means that our final answer would be the area of the remaining board is 20 centimeters. And so that is our answer. Cut and piece together 2 small squares with a side length of 1 and try to get a bigger square. So over here what we're doing is splitting each square up into 2 identical triangles. And then when you put these 4 triangles together, you get a square. There are many different ways to do this. And here are some other examples that you might want to try out yourself. So suppose the side length of the large square is A. What is the value of A? Now we're back to our square, and we know that the side length of this square is A. And so what is the value of A? Because the area of the large square equals 2, A squared equals 2. So you might ask me, how do we know that the large square's area is 2? Well, we know that this is actually 2 smaller rectangles put together to get a larger square. And these 2 smaller squares are identical. The yellow square and the blue square both have an area of 1. So 1 plus 1 equals 2. Which means that the area of this larger square is 2. And since A is the side length of this square, A squared equals 2. Then what type of number is A? Can it be a whole number? So this symbol represents because, A squared equals 2, and 1 squared equals 1, and 2 squared equals 4. Therefore, 1 squared is less than A squared, which is less than 2 squared. So A squared is between 1 squared and 2 squared. So now we're trying to find the range, the approximate range of the value of A. So A squared equals 2, right? and 2 squared equals 4, and 1 squared equals 1. So a squared is somewhere in between 1 and 4. And then now in this inequality, we just take away the exponents and we get a is somewhere in between 1 and 2. And from this we can conclude that a is not a whole number. So we just took a triangle from this square, and we call this triangle ABC. So in triangle ABC, AC equals 1, BC equals 1, and AB equals A. According to the triangle side length rules, AC minus BC is less than A, which is less than AC plus BC. So a very basic triangle side length rule is that the two smaller sides must add up to be greater than the longest side. So let's take this as an example. This is 5, the length of this side is 2, and the length of this side is 3. Can this be a real triangle? So the two smaller sides, 2 and 3, added up together equals 5, which means that this triangle does not work out. Because when I try to put these two smaller side lengths together, they will touch, but then as soon as I let go and they touch, it's going to drop down to the bottom, and it's going to form a straight line with a length of 5. The two smaller sides must add up to equal bigger than the longest side. So AC minus BC equals 0, because 1 minus 1 equals 0. And AC plus BC, which is the same thing as 1 plus 1, equals 2. So that's how we got the inequality. A is somewhere in between 0 and 2. So 0 is less than A, which is less than 2. Can A be a fraction then? We already know that A can't be a whole number. So now A has to be a fraction. So can A have a denominator of 2? So if A was 1/2, 1/2 squared would equal 1/4. 3/2 squared would equal 9/4, and so on. But we can see that this never reaches 2 exactly. 1/4 is less than the area of 2, and 9/4 is bigger than the area of 2. So can A have a denominator of 3? If A was 1/3, then the area would be 1/9, and that's too small. And you can see that over here, none of these examples lands exactly on 2. So now we're going to move to A having a denominator of 4. 5/4 squared equals 25/16. 7/4 squared equals 49/16. And as you can see, 25/16 is less than 2, and 49/16 is over 2. So again, we still can't land on 2 exactly. You might wonder, why do we not have 6/4 in here? That is because 6/4 is technically the same thing as 3/2, which was listed over here. So we don't need to rewrite that again. So our conclusion is that A isn't an integer, neither a fraction. So A cannot be a rational number. You may know that the definition of rational number is a number that can be written in fraction form. And if A cannot be a fraction, then it's not a rational number. Then what is the value of A? So this square has an area of 4 because 2 squared, this is the side length, 2 squared equals 4. And the smaller square has a area of 1 because 1 squared equals 1. So A is somewhere in between. Now for this activity, you might need to use a calculator. If you don't, it's fine because we're just exploring together. So if A is greater than 1 but less than 2, then the area S, would be somewhere in between 1 and 4. 1 squared equals 1. A squared equals its area, which is S. And 2 squared equals 4. For the next one, we have 1.4, A, and 1.5. Again, we square all these numbers. So we get 1.96 is less than S, which is less than 2.25. And we keep squaring for the rest of these numbers. And we keep getting closer and closer and more accurate, but we're never quite actually landing on an exact number. Will the side length A ever reach a point where when it is squared, it exactly equals 2? Is A a terminating decimal? What type of number is it? In the end, with the help of computers, we find out that A equals 1.41421356. It is a non-terminating decimal. Find the value of side length B, the side length of a square with an area of 5. Round your answer to the nearest 100. So this is another kind of practice problem of what we just did. Again, if you try to find the square root of 5, you're going to get another non-terminating decimal. A and B, these two side lengths, their values keep going on and on forever into infinity. But it's not like 3.11111 and it keeps going on forever. It has no pattern to it. It's basically just a lot of random numbers stacked together to form a non-terminating decimal. Use a calculator to calculate and write the following rational numbers in decimal form. What have you found? So 3 equals 3.0, negative 3/5 equals negative 0.6, 47/8 equals 5.875, 9 over 11 equals 0.81818181 repeatedly on to infinity, and 11 over 90 equals 0.122222222. 5 over 9 equals 0.55555 and keeps going on into infinity. Any rational number can be written as a terminating decimal or an infinite recurring decimal. Conversely, any finite decimal or an infinite recurring decimal is also a rational number. So all of these numbers were already going to be rational numbers because they were first given to you in fraction form. So any number that can be written in fraction form is a rational number. Use a calculator to calculate and write the following rational numbers in decimal form. What have you found? So here's our knowledge point. Non-recurring decimals are irrational numbers. For example, pi equals 0.14159.265 0.10100100001. And these numbers are irrational numbers because you can't quite express them in fraction form. Now we're going to dive into some practice. Example 1. Which of the following numbers are rational numbers? What are irrational numbers? 3.14, negative 4/3, 0.57, and 0.101, and then 3 zeros, 1, and then 5 zeros, 1. So the rational numbers are 3.14, negative 4/3, and 0.57. This first number, 3.14, is not pi. It's just the regular decimal 3.14. And our irrational number is this 0.101000010000001. So from these numbers, the whole numbers would be 0. The rational numbers would be 22 over 7, negative 1/3, and 0.3 on into infinity, and 0. And the irrational numbers are just pi. So here's some examples of irrational numbers. 1. Numbers involving pi. So pi itself is an irrational number. And if you, for example, have 2 pi, it would still be an irrational number. And so is the same for 100 pi. That's still an irrational number. There is a certain pattern, but an infinite decimal that does not circulate. So we just had the example 0.1010010001 on into infinity. It looked like there was a pattern because the number of zeros increased by 1 between each digit 1, but this is an infinite decimal that does not circulate, so it doesn't repeat. So in this lesson we learned about the concept of irrational numbers and finding the approximate value of irrational numbers with a calculator. Stay tuned for the next lesson, because in the next lesson we're going to be diving into square and cube roots.